today I'll just rewrite basically the notation that I have for a triple integral, and then it's really a lot better to look at it from the point of view of just a bunch of examples. So from last time, we kind of mentioned that the triple integral is going to be a triple integral over some solid region of some function. Now the function, since this is a triple integral, we would expect this function to have three variables. So regardless of what it's called, a, b, or c, they're all dummy variables anyways, x, y, z. We need three variables to work with. And then the volume element, like the area element dA, the volume element here is going to be called dV. And so we have a solid region. And one of the trickier parts here is to try to describe this in 3 dimensions. And then your dV, why does it keep popping up like that? Is dx, dy, dz, the differential, but in some order that may be different from just dx, dy, dz. So that's why we don't just put dx, dy, dz there, because it might be a dz, dx, dy, or d whatever, some combination of those 3 differentials in some order, because when we change it to iterated integral, then the order will be important in how you see it. So I think the difficult part is to try to visualize your solid in 3D. So when you're trying to find the limits of integration, visualizing the solid in 3D is the first important step. And then after that, what we want to do is you want to take a look at the shadow. That this is going to make. And I don't want to say the shadow it's going to make on the xy plane, because the shadow may be on the yz plane instead, or the xz plane, so it may be on a different plane. But after you do this 3-dimensional analysis of some sort, your problem then becomes a double integral that you're going to look at in 2D. And then this is, when you get to this part, then set up like a double integral. And so the inner integral will give you the limits that puts it in 3 dimensions, but the 2 outer integrals would be your like 2-dimensional double integral that we've been working with. So that's going to be our general setup for this. You're going to get a variety of problems in your homework and in your exams where you're asked to look at the region, or maybe you have a triple integral, an iterated triple integral already, and you have to backtrack and try to figure out what the limits are, and then you may need to switch limits or something like that. So we'll take a look at those types of problems as our different examples for today. Okay? All right, so let's see. Examples. So this is the section evaluating the triple integral is pretty much like the double integral. You're going to go from inside out. So I don't think we need to worry about trying to evaluate these triple integrals. Let's just go straight to a problem where we're finding a region. So let's take a look at maybe number 7. I think number 7 was the one I had pointed out. Well, maybe that's too hard. Let's start with number 7. Let's see. You guys can handle this, I hope. So this is where it kind of gets tricky, because I've been trying to stay away from having you guys visualize in 3D, but I keep saying, you know, you could try to look at how things look like in 3 dimensions, and then I would even draw it and stuff. But I'm saying, I've said in the past, the important part is for you to be able to draw something in 2D. Now, since we are dealing with triple integrals, it is going to be a step into having to visualize something in 3D. Even if you can't draw it, just be able to imagine how these things look like. And if you can't draw it, a good idea might be to the Learning Center, the STEM Center, only the computers in the back have the graphing calculator program that I use. So maybe that might be a good idea to play around with that to get some idea of how these surfaces look like. All right, so let's see. Here we have a triple integral. The integrand is 2 times x times y, but the solid, this is the main problem that we're going to try to decipher. We got a solid bounded by parabolic cylinders. Now, these cylinders don't have a z in it, and you know that these are called cylinders because they get swept up and down a z, right? They're missing your z variable, so you would draw them on the xy plane and imagine them going up in the z-axis. So I guess for now what I want to do is draw this in 2 dimensions. And what we could do is we could just imagine that they're going to go up along the z. So x squared, y is equal to x squared is your standard opening up parabola. I should have done this in a different color. Maybe blue, no, red, no, red. And then the other parabola is x is equal to y squared, and this is why we kind of talked about conic sections back in chapter 13 or wherever it was, so that or chapter 10. So whenever we run into equations like this, we would automatically know how these things look like. So this looks like it's going to be the boundary, and this will help us when we evaluate the last 2 integrals, our double integral part, the last outside integrals. And now we have z is equal to 0, and z is equal to this plane over here. It's a plane because it looks like z and x and y are not all being raised to a power, so it looks like it's going to be a plane. Now, how that plane looks like, I don't quite know, but we'll deal with it if we have to. So I'm going to try to draw this now in 3 dimensions. And let's see, we have the parabola opening up along the y-axis on the xy plane. Has a little bit of a slant there. A parabola opening up along the x-axis. And then these are cylinders, which means they go up and down. So I'm only going to focus on this little region over here because this is the little region that that they're talking about. So that region in 2 dimensions is going to get swept up and down. Now let's talk about the planes here. The plane z is equal to 0 is just the xy plane, so that's not an issue. And this plane up here, I don't know how it looks like. It looks like it would be slanted somehow. So I'm just going to randomly draw a plane over here. Now for the solid, if you can picture this, then great. If not, then don't worry too much about it. But see, if you can picture this, the solid would be something like this. Maybe I'll draw this in blue to say that this is actually the plane, and then everything inside. So how would you describe that? Looks like a pillar of, instead of a circular pillar, it looks like it's got this shape if you look at it from the top. All right. Well, how you describe it is not important. So what we want to do is we want to set up limits of integration now. We're going to have 3 variables, and the order might be important for these variables. So it looks like we have an x and a y, a two-dimensional picture of an x and a y. So I think I would say y and x would be down in the bottom. Those would be your outer integrals based on the two-dimensional picture that we have here. And then your first integral, the innermost integral, is going to be an integral with respect to z. Okay? And we should have checked if this is above the xy plane or below the xy plane, but I think this is going to be above. If we randomly pick a 1, 1, for example, this point 1, 1, 1 in for x, 1 in for y, put 1 in for x, 1 in for y, you get z is a positive number, so we know that that's going to be above the xy plane. Actually, my plane is completely wrong now that I look at it carefully. If I put 0, 0 in here, I'm going to add z is equal to 0, so the back should have been 0. So this should have been tilted the other way. But it doesn't really matter. What does matter is that when you're setting up the limits like this, we can see our z limits, and then once we figure out our z limits, that's your third dimension, we trim this down to a two-dimensional problem, and here's a two-dimensional problem where we're figuring out the x and y limits. So our z limits, what do you think the lower limit is going to be for z? 0. So if you can imagine, if you have already imagined, if you think you're capable of being able to imagine these things in 3 dimensions, imagine that you're integrating with respect to z first. You would draw a line parallel to the z-axis into the region, and then you're going to go into the region when z is equal to something. And then you're going to be inside of the region and eventually get out of the region when z is equal to something else. So those are going to be your lower and your upper limits for z. All right, so lower limit is 0, and the upper limit, we probably guess that it's going to be 7x plus y. So these are your limits for z. Those are going to be your inner limits, and then your outer limits will depend on how you're going to set this up. Now, I have this as a y first. You could have done it either way, but since I have it as a y first, I'm going to draw a line parallel to the y-axis and note when my region, when I'm going to get into my region and when I'm going to get out of my region. So it looks like I'm going to get into my region. I need this as a y is equal to function. So y is equal to, that's x squared, right? The red one. So that's my lower limit. And then I'll be into the region until I get out of my region here. Y equals to, I have to solve for y here, and that's the square root, and you know it's on the top part, so it's a positive square root of y, or x. So those are my limits for y, and then my x value goes, constants go from 0 to 1. So my triple integral is going to look like this. I have my integrand, 2 times x times y. And my dv, instead of calling it dv now, I have the iterated integral set up. My innermost integral is going to be dz. That's the first integral. And dz, I'm going to integrate from 0 to 7x plus y. That's my first integral. My second integral, going from inside out, is dy, and it looks like I'm going to go from x squared to square root of x. And then my last integral, outer integral, is dx with constant limits from 0 to 1. Okay. Now, you can figure out this integral. There's nothing fancy going on here. One thing I cannot do is I cannot split up this integral to individual integrals that we've done in the past, because this z integral is an integral of x and y with an x and y in it. So I can't take that out of the x and y, and each of these things have x's and y's all over the place, so I can't separate these integrals like I've done in the past. Okay, so be careful with doing that. All right. ... Questions? To be continued by you. Some of the books, when you get into higher math, especially higher math, I don't know how it is in the other subjects, but when you get to higher math, they prove things and then they stop at some point and they say they leave it up to the reader to finish this proof. And so that's what I'm going to be doing. I'll leave it up to you to finish the integrals. So you can either integrate it yourself, which is easy enough to do, or put it into Wolfram Alpha. This is easy enough to do. Certainly you don't need Wolfram Alpha for this. All right, let's move on to another problem. How did this problem go, by the way? Is this okay? Look manageable? I've been drawing the three-dimensional image of things that we're looking at for a while, so I'm hoping you're kind of getting used to it. And like I said, if you're not spatially inclined, you're not able to visualize these things in 3D, then that's going to be the most difficult part. The problems are still not impossible because you can probably logistically or logically look at these limits and imagine, oh, those must be my z limits, so I may want to integrate with respect to z first. And then the rest you can flatten down to 2 dimensions. Yeah.
So when you're trying to find the limits for y, you say it's x squared and then square root of x. Why don't you do the same thing with x? Why do you go to 0?
Because this is the outer limits now. And you know what we say about outer limits. They have to be constants.
But then why can't you do that for y?
Because if you have constant limits in x and y, it's going to be a rectangle. And this is not a rectangle. So A, B, C, D. So this is a rectangular region. And whenever you don't have a rectangular region, you should expect to not have constant limits for the last 2 variables.
So for this one I could have instead of using 1 dx, I could have done this 1 dx.
Yes. And then your limits here would be square root of y and y squared or something like that, some order. Okay? All right, so let's move on. Let's do another problem. I'm just doing a bunch of examples today. Let's do number 9. Here they have vertices in space, in 3-dimensional space, and so what you have to do is imagine how these things work out and how they're going to work out, and then try to picture an associated plane with this. So this has an added feature where you actually have to find the equation of the plane, because you're going to want to integrate with respect to something in z probably, where there's a plane involved. So for this one, I want to start off with my 3-dimensional picture. Take a stab at trying to picture this in 3D. And then after we get some idea of how to approach this, we might need to do some work to find equations, and then we'll bring it down to 2D. So we have a tetrahedron. Remember what a tetrahedron is? What's a tetrahedron? How many sides? It's a solid. How many sides? It's a 4-sided solid. So we can think about this. It'll end up looking like a pyramid-like thing when we see it. So let's imagine, plan for that. So we got 0, 0, 0, 1, 0, 0. That's 1 in the x-axis. 1, 1, 0. That's 1 in the x and 1 in the y. And 1, 0, 1. So I think that goes up here. So if you just connect these dots, and if you kind of drew this correctly, connect these dots, we can kind of see that region that we're looking at. More importantly, what we need to do, I mean not more importantly, but equally as important, I guess, what we need to do is we need to look at its shadow on the xy plane. So I'm going to attempt to draw the shadow on the xy plane by outlining the xy plane. And what you could do without looking at this picture is imagine the xy plane just looking at these points with just the x and the y points without looking at the z points. And then we got 0, 0, we got 1, 0, we got 1, 1, and we got 1, 0. That's this point again. So 1, 0 happens a couple of times over here. So that looks like the region that I'd be looking at is this. Okay? So now what I'm interested in, and this is going to be a flashback to the beginning of our discussion with lines and planes, is I have this plane over here, a piece of a plane at least, it's blue, and I want to know what the equation of this plane is. Maybe I should let you know what I'm thinking. I'm kind of thinking ahead also, and I'm kind of thinking I want to integrate with respect to z first, and then I'll integrate with respect to x and y. I may want to integrate with respect to y first, and I'll tell you why. Why? It's because if I integrate with respect to y first, I'm going to have a 0 to some point. Now, imagine if I said I want to integrate with respect to x first. If I integrate with respect to x first, I'd be going into this function. Whenever I say I'm going to integrate with respect to a variable first, I draw a line parallel to that axis variable, right? So with respect to x first, I'm going to go in through this line and out of this line, and it looks like neither of them are 0. And the advantage for integrating with respect to y first is that if I integrate with respect to y first, I'm going to enter through this region when y is equal to 0. So I'm more interested in having a 0 for my limit than not having a 0 for my limit. So if you can look ahead that way to try to anticipate, I want to integrate with respect to this variable first, if I have a choice. In this case, I do have a choice. And so I'm going to integrate with respect to y. I'll dig into this a little bit later, and then your outer integrals are going to be constants with respect to x. Okay, so our first task is try to integrate with respect to z first. If I integrate with respect to z, it looks like I'm going to enter through my three-dimensional region when z is equal to 0, and exit through my three-dimensional region when z is equal to this plane. So that's my task, is to try to figure out what that plane is. All right, so before we move on, let's focus on this plane. How am I going to find the equation of that plane? Well, that plane, I have some information about this plane. It looks like I have 3 points on this plane, right? When you find 3 points, you should be able to come up with a plane. And one way to come up with a plane is to assign a couple of vectors that are on the plane, cross it, and you get your normal vector, and then use that information to follow it up. So what we're going to do is we're going to assign these vectors. Let's call this, I don't know, v is equal to, now this vector goes from 0, 0 to this point on the xy plane. When that's another point when z is equal to 0. That's 1, 1, 0. So if you do head minus tail, since your tail is 0, then that's just the point, and the vector is essentially the same thing. And I have another vector over here we'll call u, and that points to this point, which is on the xz plane. So the xz are both equal to 1. It's not moving along the y, so it's 0. So this is my other vector, 1, 0, 1. So I want to find a normal vector, and it really doesn't matter which way my normal vector is pointing, this way or that way. But your n vector is going to be given by the cross product of the u vector and the v vector. And like I said, the order doesn't matter because we're going to make an equation of a plane. So equations of planes, the orders of these things don't matter. All right, so let's cross it. I, J, K. It doesn't matter which one goes first, so let's put that one first. Let's put the u in first and the v in first because that's how we wrote it. And in the I direction, I have -1. So it looks like I'm going to be pointing this way because my x direction is going backwards in a negative direction. So it looks like I identified the correct one. With respect to j, I have a negative with a negative, so that's a +1. And then in the k direction, +1 also. And it kind of jives with my picture, and it looks like I actually did choose the correct normal. All right, now that you have the normal, just put it into the formula. And there's many formulas for the equation of the plane, right? So one formula that I can remember is -1 times x plus 1 times y plus 1 times z. Those are my normal vectors. And then for the d, I'm dotting my normal with any point that I have on the plane if I look at this as a point. Point is a vector. Now, I see that the 0, 0, 0 is on my plane, so that would be a nice candidate to use. So if I dot n with 0, 0, 0, then I'm just going to get 0 there, so that's easy. By the way, these are the points on your plane. So 0, 0, 0, this one, and this one. This point is not on the plane. This point 1, 0, 0 is down here, and it's not on the plane. So I have these 3 points to choose from. So any of those points that you choose to dot with the normal, you should get 0. All right, well, it's not quite what I want. What I want is a z by itself, so that's easy enough to do. We've got x minus y, I think. Z is equal to x minus y. And that will give us a z is equal to function to be my upper limit for my inner integral. So it looks like my z limits are going to go from 0 to x minus y. Good? All right, now let's examine the y limits. So we got started with this. We agreed that integrating with respect to y is good because that's going to give us a 0. Y is equal to 0 line over here. And then now you're going to be inside of your region until you get out of this region when y is equal to what? So this is 0, 0, and 1, 1. We know what that line is, right? Y is equal to x. So that's just the x equals y line. And if you don't know that, then do the point slope formula and come up with the y is equal to x line anyways. All right, so that is your upper limit, y is equal to x. And then your outer limits for the x are constant. And you just look for the numbers where it starts and stops. 0 to 1. Okay? Questions? So that's the hard part. Now it's translating it to a triple integral, and this part should be pretty easy. I got my my integrand is 6x, y, z. My dv is going to be a dz first, where my z goes from 0 to x minus y. My next limits are in y, where y goes from 0 to x. And then my x limits go from 0 to 1. Okay? Again, these are all polynomials when you integrate it, so it should be a piece of cake. Questions? All right, let's do some more. This is fun. Now, I was looking at number 10. I was kind of interested in it because this is one of those ones where, you know how we usually, a lot of times we integrate with respect to z first, and then with respect to x and y. So this is one of those cases where it doesn't look like you're going to integrate with respect to z first. So let's take a look at this. Number 10 is a triple integral where the solid is bounded by a paraboloid. And again, you know, from the conic sections to the conic sections in 2D to the quartic sections in 3D surfaces. You should be able to look at these surfaces and be able to imagine how they might look like. So the paraboloid is x is equal to 5y squared plus 5z squared. This looks like it's going to be circular paraboloid, but it's going to be opening up in a different direction. Not up along the z or down along the z. It's going to be opening up sideways somehow. And we have to figure out which way it's opening up. And then there's a plane x is equal to 5. So we got z is equal to constant planes are going to be horizontal planes when z is equal to something. But when x is equal to something, this is going to be parallel to the yz plane. And we have to figure out where that is. On top of that, we have to figure out where they intersect. So that's going to be another challenge. All right, let's start with this paraboloid. This paraboloid, x is equal to something with a y squared and x squared. So now they're both positive y squared, positive z squared. And this is in the x, so it should be opening up in the x direction. Is it opening up in a positive x or negative x direction? Looks like it should be opening up in a positive x direction, right? And then it's going to be, this is your x axis over here, so it should be opening up in the positive x direction like this. Okay? So that's the paraboloid. And then I have a plane, x is equal to 5, so if you just imagine where 5 might be, maybe I would imagine 5 to be over here. Just put a cap on that paraboloid to make it stop over here. So this looks like a standard paraboloid that's been chopped off, and then we can actually look at this as if it was opening upward if we wanted to, but I think it's a good idea and good practice to look at it going sideways to see how our what do I want to say? Our order of integration is going to work. So we're not always going to be integrating z and then y and x. In this case, what are you interested in integrating with respect to first? X probably, and we'll take a closer look at why that is. And at this point, the other two, we're going to need to take a look at them in 2 dimensions. And since we're going to integrate with respect to x first, our 2-dimensional problem will be the other 2 variables that we're not using, so y and z. And what you need to do is imagine what the shadow of this is going to look like on the yz plane. Can you imagine what the shadow of this might look like? It's going to be a circle. Okay? It's going to be a circle. Now the next task is to figure out, this is going to be a circle on the yz plane. it looks like it's basically this circle, except we're going to move it to the YZ plane. Maybe I should have done this in red. It's going to be a circle on the YZ plane, so that's just basically this circle that will get moved to the YZ plane. So the question is, what is the radius of that circle? Any ideas on how to find that radius? Remember, this circle came from the intersection of the plane and the paraboloid. So any ideas on how to find that? Plug and chug. 5 for x. Yeah. So you guys already got that. So you combine these two. X is equal to both of them, so put 5 in for x. 5 is equal to 5 y squared plus 5 z squared, and then we have y squared plus z squared is equal to 1. So it looks like it's going to be a circle of radius 1. Now, how you want to deal with that is your own business, y and z. But I have a suggestion for this. What's my suggestion? Go polar. Right? It's circle. But let's set it up in Cartesian coordinates first. And then we'll talk about going into polar coordinates after we get this integral set up. All right. Now we're back to this three-dimensional region. I'm going to redraw my paraboloid and my plane. And now I want to integrate this with respect to x first. So just like I've been doing with 2 dimensions, we can do this in 3 dimensions also. And maybe you can just see it from here. But if I'm going to integrate this with respect to x first, I need to know what my lower limit is for x. I would draw a line parallel to the x-axis. I would need to know when I'm going to enter my region, and then I'll be inside of my 3-dimensional region and eventually get out of my 3-dimensional region by hitting another surface. So I'm looking at 2 surfaces. One's the paraboloid, one's the plane. Which one am I going to hit first if I go from negative to positive along my x? It's the paraboloid, right? So that's going to be the lower function for my x limit. So 5x squared plus 5z squared. This should be y, sorry. 5y squared plus 5z squared. X is equal to that function or surface when I go into my region. And then x will be inside of the region until I get out, and I get out when x is equal to 5. So those are my limits for the inside. All right? Now for my limits in the YZ plane, I put down that I want to integrate with respect to y first, so let's do that. Let's integrate with respect to y. I'm going to draw a line parallel to my y-axis, and I'm going to ask myself, what functions am I going to go into, and what function am I going to get out of when I'm looking at my region here? So I'm going to get into this function over here. What is the equation of this function? And I need a y equals. What is the equation of this function? Y equals what? Square root of 1 minus z squared. So we're in y and z now. So this is x squared plus, or I'm sorry, this is y squared plus z squared is equal to 1. And if I'm looking to solve for y, I solve for y here. Now, my equation that I put here isn't quite correct, right? What should it be? It should be a negative, because I'm going into the negative side, and then I'm going to get out on the positive side. So those are my limits for y. So negative square root of 1 minus z squared, positive square root of 1 minus z squared. Okay? Outer limits are constants. What are they? What? Negative 1 to 1. Okay? You can see that these integrals don't look very nice, but we'll write it down anyways. So I have my 3 integrals. My integrand is 10. I should have made a little bit more room for the second integral. There it goes. 10x, and I integrate with respect to x first. dx integral from the lower limit is 5y squared plus 5z squared, and my upper limit is just 5. That's my dx. And then I'm going to integrate with respect to y, and my y limits are negative square root of 1 minus z squared to positive square root of 1 minus z squared. And then I'll integrate with respect to x, z, from negative 1 to 1. And these are my iterated integrals. I don't see getting away from doing, moving integrals around as constants and stuff, so it looks like we're stuck here. This is the best we can do. Okay, so I think when you integrate this with respect to x first, you're going to get an x squared, and then when you put these values in, I think this actually might be doable, doing it by hand. But my idea would try to change this up force this into polar coordinates somehow. Probably after your first step in your integral, because you have to integrate this. Okay, any questions? So we may return to this particular problem, if I remember. We may return to this particular problem tomorrow, when we're going to be talking about changing coordinate systems. Now, in 2 dimensions, we're able to change from Cartesian coordinates to polar coordinates, and we just call it polar coordinates. In 3 dimensions, there's an equivalent, analogous change of variables into what's called cylindrical coordinates. So that's what we're going to do tomorrow. And if I remember, we'll use this very same problem where we got most of the work already set up, and then we'll just redo this problem in cylindrical coordinates. Okay, questions? All right. So that's another one that I really wanted to do. There's one more where they want you to set things up in different coordinate systems. Solid, sketch the solid. Ooh, look at that. Number 17. Let's do number 17. And so this figure Shows the integration for the integral of this thing. And so this must be your E, your volume E. So they want you to rewrite this triple integral. Let's put E here. And they want you to rewrite this triple integral of f of x, y, z dv. They want you to write this in different orders. So originally this is an order of z and then y, then x. Then we want to switch around to z and x and y, and then maybe y and then x and z, and then all that stuff. So looks like it's going to be fun. All right. So I don't know if you need to do this, but being able to picture this is great. Now, since they have the picture for us already, that makes it a little bit easier for us. But if you didn't have that, then you would probably want to take this in steps and try to imagine how this thing would look like. Z first, and then y, and then x. So I think it's always good to rewrite these inequalities in the order that you want them, and then when it comes time to changing the order, then rewriting them. But I will have to warn you that when you change the order, you don't just switch your order, because remember our rule that our last or outer integral is always constant. So it's a matter of taking a look at these things down and flattening them out in 2 dimensions and stuff. So according to what they have, we have z is equal to 0, and z is equal to 9 minus y. They actually gave you that information down below here. Z is equal to 9 minus y is one of the equations. Y goes from the square root of x to y is equal to 9, a constant. And then your outer limits for this particular integral setup goes from 0 to 81, constants. So now let's change the order of integration. The easiest thing to do probably is change the x and y for now. So let's do that. So there's 6 possibilities in all. Is there 6 or 8? There's 3 numbers and you're switching the order, some permutation. No, but there's only 6. I think there's 6 possibilities for this. 2 times 2 times 2, or 3 times 2. 3 times 2 times 1, thank you, yeah, that's it. What's that? That's the permutation or something, right? 3 factorial. All right, so we have 1 order already that they provided, so we are looking for 5 more different orders. So let's do this one where we're integrating with respect to z again first. And because we're integrating with respect to z again, I think our z value is not going to change. And then we'll just change the order of x and y. So we're always going to look at the same 3-dimensional picture, but once we figure out the third dimensional limits, we're down to x and y. So what we want to do here is take a look at x and y. It looks like this is going to be in the first octant and first quadrant. So just imagine how this is going to look like on the xy plane. So it looks like I have this curve over here, which looks like y is equal to x squared, or y is equal to square root of x, I'm sorry. I was going to say x is equal to y squared, but it's only the top part, so that's y is equal to square root of x. Should do this in red. And then you have y is equal to 9, I think, wasn't it? Y is equal to 9. And you have to make sure you identify the correct region. X, it didn't matter. Well, it did matter because that's our constant limits for our original setup. X goes from 0 to 81. So that does make sense that this is 9 and this is 81. But now I'm switching orders, so I'm going to go integrate with respect to y first. Oh, let me put the z. The z's didn't change. This is still going to go from 0 to 9 minus y. but now the x and y will change. I'm going to integrate with respect to x first, and I'm going to draw a line parallel to the x-axis. And I'm going to enter my region when x is equal to it's the square root of x. Y is equal to the square root of x, right? But I want to solve for x there because I'm drawing. Oh wait, sorry. Never mind. I did something. I'm supposed to integrate with respect to x. So I want to draw my line like this, right? Sorry about that. So integrate with respect to x. I'm going to draw a line parallel to my x-axis, and so this one's easy. Let's integrate with respect to x. X is equal to 0. And then I'm going to get out of my region when x is equal to, and here I would solve for y is equal to the square root of x. I would solve for x there, and I get y squared. So that's going to be my upper limit. The y are constant limits. Y goes from what to what? 0 to whatever the y value here is, right? Not 81. It's actually 9. So 0 to 9. So this would have been an easier integral because I have zeros for my lower limits. Here, the second integral here, it didn't have a 0. So that would have been tougher to integrate. So here is one way of doing it. Okay. Now let's integrate with respect to what first? Y. Once we integrate with respect to y, then the other two, you can figure that out in a minute. But let's just say x and then z. So to integrate with respect to y first, you need to look at your big picture. And then to integrate with respect to x and z, you need to look at the shadow that this is going to make on the xz plane. Okay? So I'm going to draw this integrating with respect to y first in green. And what I would do is in my three-dimensional region, I would draw a line parallel to the y-axis and imagine what region or what surface am I going to get into when I get into my region, and then I'll eventually hit another surface to get out of my region. So when I draw a line parallel to the y-axis, I'm going to hit two surfaces, one going into the region, one getting out. So the question is, what are these two surfaces that I'm hitting? All right, the first one, I want y is equal to a y equal to surface. So what's my surface for this first one that I'm getting into? So y is equal to square root of x, right? That's my only y relation. This is a cylinder going up. Y is equal to square root of x. So that looks like it's going to be my lower limit. Now I'm going to be in the function and then eventually get out of this function on this plane. Now this is a plane z is equal to 9 minus y. But since I'm integrating with respect to y first, I'm going to want to describe this plane as y is equal to something. Right? So what's y equal to? 9 minus z? Yeah. So 9 minus z is going to be my upper limit for y. We good with that? All right. Next thing we need to do is we need to take a look at the shadow that this is going to cast on the y, on the xz plane. So on the xz plane over here, imagine how this is going to look like. It looks like I'm going to, let's see, cast my shadow, cast my shadow. I'm going to go as far as here. Anybody know what this point is in the x? X is equal to? What? No? I think it's 81, right? This thing, y is equal to 9, this thing goes all the way up to 81. So this picture is not drawn to scale. So I'm looking at 81 over here. My z goes all the way up here. What's this equal to? How do I even find that? What? 9? How did you guys get 9? So this is when y and x, both x and y are equal to 0, and it looks like it's associated with this plane. And so when y is equal to 0, z is equal to 9. So that is going to be my upper limit over here. Now, the question is that if you shine a flashlight here, this is going to make a shadow on the xy plane and on the xz plane. And so the question is, what is the shape of the shadow going to look like? Is it going to be curved? Is it going to be a line? And so somehow what we're going to want to do is we're essentially looking at this intersection. It's a matter of intersection again, right? We're going to look at this intersection between the surface y is equal to the square root of x and the surface z is equal to 9 minus y. And somehow put those two together in some logical way that would give us an equation of x and z. Do you understand what I'm saying? We got these two equations, y is equal to the square root of x, and z is equal to 9 minus y. Now, what would a logical way be to combine or to set two things equal to each other? Because whenever we want an intersection, we want to set two things equal to each other, and I'm saying that in air quotes. How are we going to set two things equal to each other here? So y and y is equal to the square root of x, so why don't we put that in for z? So we get z is equal to 9 minus square root of x. Now, is this what we were looking for? I wanted a z and an x relationship that this is going to cast on the plane. And this looks like it's it. So z is equal to 9 minus square root of x. Square root of x function goes like this. The negative square root of x means you're going to reflect it around the z. And then the 9 minus that means we're going to move it 9 units to the right. So it looks like it's going to be this. So we got these points of intersection, x at 81, z at 9, and then this graph, z is equal to 9 minus x squared, or square root of x. All right, so I think we're ready to find the limits with respect to x first. With respect to x first, I draw a line parallel to the x-axis. I go into my region when x is equal to 0, right? I get out of my region when, I have to solve for x here. Can you do that real quick? Z minus 9, negative 9 minus z squared. I got 9 minus z squared. Is that right? If I solve for x here. So that's going to be my upper limit, because that's where I get out. And then my z limits are constants going from 0 to 9. Okay? So this is probably the most difficult one. And once you know this, if you integrate with respect to y2 first, you're going to essentially get the same region. So I think it would be almost the same. So square root of x, 9 minus z. So those are your y limits. if I draw a line parallel to the y-axis or z-axis, if I'm integrating with respect to z first, I'm going to go from 0 to z is equal to 9 minus, it's already solved for here, right? Z is equal to. And then my x goes from constants from 0 to 81. Okay, so I'm hoping with respect to x first wouldn't be bad just by looking at the graph, the three-dimensional graph. It looks like you're going to have a triangle for your two-dimensional picture in the y and z plane. And then x looks like it'll start with 0, and then it'll come out of this x is equal to line. All right? Was that fun? Woo! Yay! All right, tomorrow we're going to take these triple integrals into another coordinate system. And you know that stuff that I talked about on Thursday? It looked like I was just kind of bullshitting around. It's actually, the change of variable in Jacobian is actually covered in the section 10 in this chapter. And so I'm going to, I hope you guys paid attention, even though it sounded like it was just for fun. It's for fun, but it also, we're going to use a Jacobian in 3 dimensions. All right, see you guys tomorrow. Oh, quiz now is going to be due tomorrow. I'll update it, and I'll send an announcement right after I update it so you know when to download it.
Yeah.